when we talk about AI, we love big numbers, right? A self-driving car that's 99% safe, a spam filter that's 99% effective. It sounds amazing. But what if I told you that 99% accuracy can be, well, dangerously misleading? Today, we're going to explore how we really measure AI performance and why that big, flashy number can sometimes be nothing more than an illusion.
So let's start with this. Imagine you build an AI model, you test it out, and boom, it comes back with 99% accuracy. I mean, your first instinct is probably to pop the champagne, right? It sounds like you aced the test, a total success. But is it really? Okay, to see why that 99% might be a trap, let's imagine we're building an AI to detect a pretty rare disease, one that only affects, say, 1 out of every 100 people. Now, what if our model decides to take a lazy shortcut? What if it just predicts no disease for every single person it sees? Well, think about it. Since 99 out of 100 people are healthy, the model is going to be right 99% of the time. And here's the kicker. That 99% accurate model, it has a 0% success rate at its actual job. It completely fails to find even one person who actually has the disease. For something like a medical diagnosis where finding that one positive case is literally the whole point, this model is completely and utterly useless. This right here is the accuracy illusion, and it happens all the time when you're dealing with imbalanced data.
So, to get past the simple accuracy trap, we need a better toolkit. It all starts with understanding a really simple idea. For any prediction an AI makes, there are really only 4 possible outcomes. 2 ways for it to be right and 2 ways for it to be wrong. Let's break them down. First up, the true positive. This is the perfect score, the bullseye. The thing we're looking for, let's say it's a spam email, is actually there, and our model correctly spots it and says, yep, that's spam. It's a true hit, a win. Next, we've got the false positive. You might also hear this called a type 1 error. This is when the model thinks it found something, but it's totally wrong. It's the fire alarm going off when there's no fire. In our email example, this is that really important email from your boss getting flagged and thrown into the spam folder. It's an annoying mistake for sure. Then there's the true negative. This is the other kind of success. The model sees a normal, non-spam email and correctly recognizes, hey, this is fine, and just leaves it in your inbox. Everything's working exactly as it should. No drama. And finally, we have the false negative, or a type 2 error. Now this is often the most dangerous kind of mistake. This is that sketchy spam email that slips right past the filter and lands in your inbox. Or going back to our disease example, this is the absolute worst case scenario. The model tells a sick person that they're perfectly healthy. It's a complete miss, and the consequences can be huge. So, how in the world do we keep track of all these? Well, we use something called a confusion matrix. And don't let the name scare you. It's basically just a scorecard. It's a simple little grid that shows you what the model predicted versus what was actually true. All the correct guesses, our true positives and true negatives, land on a nice, clean, diagonal line. And all the mistakes, the false positives and false negatives, they fall off that line, showing us exactly where our model is getting, well, confused. This simple tool is the foundation for everything that comes next. Okay, so now that we have these 4 building blocks, we can build 2 of the most important metrics in all of machine learning, precision and recall. Now, the tricky part? They're almost always in a tug of war with each other. If you try to improve one, you often end up hurting the other. It's a very delicate balancing act. Let's look at them side by side. Precision looks at every single item the model flagged as positive and asks a simple question. Of all the things you flagged, how many did you actually get right? It's all about avoiding those false positives. Recall, on the other hand, comes from the other direction. It looks at all the items that were truly positive out there and asks, of all the stuff we should have found, how much did you actually catch?
Its main goal is to avoid false negatives.
Let's put that another way. You can think of precision as being the perfectionist. When it makes a positive prediction, it wants to be absolutely, positively sure that it's correct. A model with high precision is super trustworthy. When it says yes, you can believe it.
Recall, though, is more like the thorough detective. It doesn't want to miss a single clue. It casts a really wide net to make sure it finds everything it's supposed to. A high recall model is great at finding all the positive cases out there, even if it means it makes a few extra wrong guesses along the way.
And this brings us right back to that trade-off. Let's go back to the spam filter. If you make your filter super, super strict to get high precision, that's great. No important emails will ever end up in your spam folder. But you'll probably miss some of the sneakier spam emails, which means your recall goes down. But if you loosen the rules to get high recall and catch all the spam, you're going to accidentally flag some good emails by mistake, and that hurts your precision. See? It's a constant push and pull.
So, if you can't have perfect precision and perfect recall at the exact same time, what do? You have to find the sweet spot, the best possible balance between them. And that is exactly what our next tool, the F1 score, is designed to find. It's the elegant solution to this whole balancing act. The F1 score gives you a single number that cleverly combines both precision and recall into one. But here's the cool part. It doesn't just take a simple average. No, it uses a special kind of average called the harmonic mean. And that gives it a really unique and powerful property. So what on earth is a harmonic mean? Well, the main thing you need to know is that unlike the average you're used to, the harmonic mean is heavily influenced by smaller numbers. So if one of your values is really low, it's going to drag the whole average way down with it. And that property is exactly what we need here.
And this is why it's so perfect for this job.
Some of the most popular metrics like accuracy and another one called the F1 score can be totally fooled by this kind of imbalanced data. And here's why. Accuracy just lumps all the correct guesses together, right? So that huge number of true positives just completely papered over the fact that there were 0 true negatives. But the F1 score? Oh, it has an even bigger problem for our situation. Look at the formula. It's built using true positives, and false negatives. It completely ignores true negatives. That means it literally has no idea if the model is any good at all at identifying healthy people. And this chart just says it all, doesn't it? Both of these super common, widely used metrics are giving our totally broken model a fantastic report card. Accuracy is at 90%, and the F1 score is even higher at 95%. I mean, this isn't just a little misleading. In a medical situation, this is actually dangerous. The researchers whose work inspired this explainer, Chico and German, they just nailed it. They said relying on these metrics can give dangerously over-optimistic, inflated results. And that right there is the accuracy trap. So, you're probably wondering, is there a better way? Is there a metric out there that can't be tricked so easily? Well, thankfully, yes. And it's time to introduce the hero of our story, the Matthews Correlation Coefficient, or just MCC for short. The real superpower of the MCC is that it's the only common metric that absolutely requires a model to do well across the entire confusion matrix. To get a high score, you need a lot of true positives and a lot of true negatives. It simply can't be fooled by a model that's only good at one thing. All right, let's put it to the test. This is the moment of truth. We are going to apply the MCC to the exact same flawed model that somehow scored a 90% on accuracy and a 95% on the F1 score. What's it going to say? And there it is. Look at that third bar, the Matthews Correlation Coefficient. The MCC gives our model a score of negative 0.03. That's basically 0. The MCC instantly saw what the other metrics completely missed. It correctly identified this model as pure garbage, no better than just flipping a coin. It saw that 0 in the true negative box, and it sounded the alarm, loud and clear. And just to give you some context for that score, the MCC scale is super intuitive. +1 means a perfect prediction, -1 means you're perfectly wrong every time, and 0, right where our model landed, means your AI has absolutely no correlation with reality. It's useless.
Now, I know what you might be thinking. Okay, that's a neat little theoretical problem. But the source paper for this shows this exact same thing happening with real-world medical data. Let's take a quick look at a genomic study that was trying to classify colon cancer tumors.
So when the researchers ranked all the different AI models using the F1 score, the #1 performer was a model called KNN. And yeah, it was fantastic at finding cancer, a 92% true positive rate. But look at its weakness. It only correctly identified healthy patients about half the time. The F1 score completely hid that huge flaw. But when they ranked everything again by MCC, the winner was a different model, gradient boosting, a much more balanced and reliable model that was good at finding sick patients and good at clearing healthy ones. So let's pull all this together. What does this actually mean for you the next time you see some headline about a new AI with 99% accuracy? Well, it means you've got to look beyond the hype. So let's just quickly recap the big takeaways here. #1, remember that a high accuracy score can be a total illusion, especially with imbalanced data. 2, the super popular F1 score has a massive blind spot because it just ignores true negatives. 3, the MCC gives you a much more truthful picture by demanding balanced performance. And all of this leads to the most important point of all. You should always ask which metric is being used to judge success, and think about what it might be hiding. You know, at the end of the day, what we're really after isn't just a big, flashy number we can slap on a press release. The real goal is a score that tells the truth about how a model performs, its strengths, and maybe more importantly, its weaknesses. So, I'm going to leave you with this. The next time you see a headline or a product claiming some unbelievable level of AI accuracy, what's the first question you're going to ask? Because now you know that the most important details are almost always hiding just beneath the surface.